setup. Okay, so some people had noticed and had questions about like, hey, how do I access the videos? I just deleted them, so it doesn't really fix where the videos are, but the link is not there for you to not get to it anymore. But there are these broken links. So it's a work in progress. I'm slowly refilling all the things that the shift from Google to Microsoft took from me, but one day it'll all come back. That was just a quick logistic update for today. Anything else coming up as we're starting up on the class? I saw a previous student today at coffee shop. He said silver lining from like less TA support is that there's less assignments. Have you noticed that? Has that been better? Life is better? Maybe it's like the universe just telling us like, dude, slow down. You don't need like 15 exams in order to prove that you did this, that you understand this work, to learn something, right? So I don't know. Maybe that's what this is. It's just like chill out, do the basics, get things done, go home, go enjoy the day, go play in the snow. We could do that. Does anyone have more assignments? Less TAs, more work? Now it's a round robin, you grade each other. Like we don't have any TA support, so go do that work yourselves. Should we do some design work? Friday afternoon, the best time to start a new problem? Because you're like laser focused. There's nothing else in your life. I must get through this engineering work. I was up until, it's not like I wasn't up super late, but I skipped dinner as I was putting together an IKEA dresser. It just took forever. And just aligning things and putting things together. They do a great job of engineering. You don't need any power tools or anything, but man, it just takes forever. It's just like installing and doing stuff, and then it's 10 o'clock at night. I'm like, I didn't even eat dinner. So then I'm like sitting down to eat dinner. But my wife said, it's like a hyper-focus thing. Like you're either on or you're totally not there. So here we go. So this is our first case problem, like a problem to work on. Like an actual kind of engineering problem. And it would be like a real kind of design. I simplified it down into just like, we're just trying to stop something. So there would be more depending on what field you're working on, this kind of thing. But you would have to weigh some different options. Like we have options A, B, and C. We can either use a spring, we could use some fluid, or we could use like friction, like somehow slow this thing down, bring it to a stop with friction. So, what do? Let's just take a second and look at it, try to think about like, what are your initial thoughts on approaching this? One of the things, so here I'm saying like, create some graphs of what happens to these blocks. Maybe this is like your manager, like show me. Like you think it's gonna work, prove it. So that's kind of our final goal is like, make some graphs, what's gonna happen. So what would the graphs even look like? What's your like initial gut reaction to this kind of design problem? And this is going to be similar to the self-assigned groups for this project as well. So you can work with other people. You have to work with other people because you have to submit it together. But initial thoughts, let's just take 30 seconds, talk to somebody? What are you thinking? Yeah. Okay, so Y direction is going to like change. Yeah. Okay. Which one do you think is going to go like the furthest? Yeah. Okay.
The stopping meter
Okay.
for blocks and
Okay. All right. Something's going to stop it.
Yo, I'm trying to analyze this.
Jump straight into the numbers.
So see this one, this one's probably, you didn't even read. This one's probably a stop. This one's probably a stop. And this one's probably a stop.
So what is that? Bro,
I think it's which one's more efficient. Or what if the frictional forces has a greater effect on
oh, wait another number.
it? Literally does.
Oh, this.
Yeah, the spring has a pain.
I'm saying B8.
Yeah, he's definitely gonna be most efficient. Because it's got a B. I don't know what B is, but it's 5 kilograms. This is 0.1 kilograms. So I think it's gonna stop. That might as well be yes, we do.
Well, you know that house over there. This goes be
It's 100 newtons of force. Because that's what the K value for the spring is. I know K is. So yeah, it's not 100 newtons.
You brought my shit.
Okay, so we had, I don't want to like just leave you off for too long. We had a little bit of time. Some things that came up so far in just my quick snapshots of what people were thinking was like, one question was, what kind of graphs? Like you're told, make some graphs. With graph what? What would be important to graph here if you're making like a stopping, if you're trying to say this stopped something? Maybe distance and time. So at some point the distance hopefully stops distance. Yeah.
I was gonna say that.
Distance and time. Okay, distance, time. Done. Just distance versus time. And everything else is self-explanatory. A true engineer can look at a graph and take derivatives of it and be like, ah, yes. I see the zero there. One suggestion, oh, sorry, go ahead. Energy, so that was the other suggestion that came up, was like, what if we had kinetic energy of like, after it hits this stopping mechanism, what does the kinetic energy look like? Which was also, it's tied directly to speed, right? Like how fast is the thing moving? So if your kinetic energy goes to 0 or your speed goes to 0, you know it did come to a stop. Okay, cool. Then I asked up front, like, which one do you think is gonna stop? Yeah, or which one's the best stopping mechanism? And the answer was, it depends. It depends on a lot of stuff, right? So it depends. Have to do some calculations, like jump into the numbers, I guess. Will all three of these bring the object to a stop?
I hope so.
Hopefully, right? Yeah, hopefully. Have you ever dropped like a marble in a pool? Or I guess dropped anything into a pool. A penny, a toy pedo, or I don't know. What happens when you drop it into the pool?
It sinks.
It sinks, yeah. Does it speed up when it hits the water?
Not necessarily.
Usually doesn't speed up, right? So it's definitely gonna slow down. Okay, so we'll come back to it. What about dropping it into like something with friction? Is friction gonna stop it? What? It could, yeah, maybe, it could. What do we think? Is there a bottom? Maybe that's part of what we need to say is, right? Like, hey, look, we can't. We need to design a bottom, and maybe that bottom has to be a certain distance, right? So, like if we only had a pool that's like a 1/4 inch thick, and we're trying to stop, I mean, it's half a kilogram? I think half a kilogram. So a 1 pound slug that we're trying to stop with an inch of water. It's like, nah, like that, it's just gonna splash the water right out. But if we give it like a foot, then maybe it'll slow it down enough where it comes to rest. Maybe, I don't know, we'll find out. Any other initial, what else did people, there must have been like questions or initial thoughts. Brainstorming phase, no bad ideas, just shout them out. Kittens.
It's a bit like difficult to really know for sure whether B will float or sink because we don't have the volume of the block to like properly get the point.
Oh, so you're worried about buoyancy? Okay, yeah. Yeah, we don't know like density of the water. Roughly, so let's say it's a point mass. What's density of a point mass? Or sorry, what is a point mass? Not a pointless mass, a mass that has a point, just one point. What makes it a point mass? Yeah.
You consider the object to be a single point and not have dimensions.
No dimensions. Okay, maybe no dimensions.
Like it doesn't fill up any space. Instead of just a point.
So zero space. Zero space is a point. Maybe. Yeah.
I would say where all the mass of the object is concentrated, so we just count it at that particular point.
Okay.
Different point.
Yeah. It's all concentrated. This is actually like a really, so a lot of times you're just kind of told like treat this object as a point mass, but did you ever really stop and think like is this a point mass? Can it be considered a point mass? So baseball, you throw a baseball, can you consider that a point mass? Can you use kinematic equations to model like x of t is v0t plus or minus 1/2 gt squared? Can you say that about a baseball? Yeah. What about the fact that it's not a single infinitely dense point, right? It's definitely, you can hold it. It's got a size. So what's the difference between baseball point mass? Yeah.
One issue you have with certain things with point mass is that certain things depend on the area of the skin.
Okay.
Like on the aerodynamic side, it's going to depend both on
Yeah.
change in orientation and its area.
Yeah, that one, oh my god, I look it up at least 10 times a year and then I always forget what it is. But the spin, by spinning a sphere in a fluid, if it's moving forward and spinning, you can create differential pressure and lift. Like bend it like Beckham sort of effect. So curveballs, knuckleballs, like depending on how spin works. Okay, so aerodynamics, that affects, but it doesn't really change whether or not it's like a point mass in terms of dynamics, right? Like it's just something that has area. Yeah.
I think it also has to do with like the material distribution and like types of materials. So like
Okay.
if it's like a weighted ball and there's most of the mass is on one side and there's some other smaller mass you can't really consider it.
Yeah, so how that mass is distributed lends to the fact of whether or not you can say this is a point mass. So if you think about like throwing a hammer versus throwing a baseball, both of them center of mass is going to travel in that parabola. But the hammer is going to have it's going to look very different in the air than a baseball. And so part of that is that baseball is very symmetric, like all the mass is, for the most part, pretty uniform around it. But as far as like dynamics is concerned, whether or not you can say it's a point mass has to do with whether or not you care that the orientation is changing. So with a hammer, the top of the big head of the hammer is very different than the bottom leg of the hammer. You care if you're getting hit by that or or hitting something, I guess. Or axe throwing. Maybe axe throwing would be better, less violent, just into a wall, a target. You want the axe head to hit the target, not the butt. So there, we care about orientation. We would want no point mass. Yeah, but anyway, so if we consider like buoyant, like it's dense enough that buoyancy is not a big factor, then we could roughly say buoyancy is 0, or we could include it and say we need to figure it out later, something like that. Cool. Other thoughts? Initial thoughts? Brainstorming thoughts? Yeah.
I thought just like on the option where you have friction, depending like on the two materials, you could cause damage to the object, so that's also something to consider in design.
Okay. Yeah, friction is definitely like a wearing, like things that are rubbing is a wearing process. So we could be causing damage depending on what we're talking
It could
about.
also be true for like the water
could be, yeah, yeah. So with, like if in a surface where you expect friction, so like brake pads. Like brake pads are friction using friction to your advantage to stop you when you need to. So you put a sacrificial brake pad in there so that you wear down brake pad, you know you're gonna wear it down, and you don't wear away your nice metallic rotor, and now throw out the brake pads, install new ones, and now you got a nice new surface, bed them in, now you're good to go. At least if you are wearing away your rotor though, like as you're using brake pads. It is a two-way street, it's just you wear more brake pad than you do rotor. Cool. Good thought. Yeah.
I think we just also did like the height of all of these things, like the spring or like the height it's going down.
Okay, yeah, so far what we have, so we know M is, what was it, half a kilogram or 0.1? 0.1, sorry. So it's not a pound, it's a fifth of a pound. Fifth? No, 0.1 pounds. No, 0.2 pounds. Oh my god, whatever. It's something. So we know the mass. The rest of the world is all like into the future with like, yes, we've all embraced the metric system, but here in the States, we're like, no, we're gonna stick to our horse and buggy, like horsepower units and slugs and BTUs, all this great stuff. And then we know we're dropping 0.5 meters. We don't know how deep these are going, and maybe that's part of this exercise, right? Like, we want to know, like, if you drop it onto that spring, how long does that spring need to be? Because longer spring can still have the same spring constant. It just does, but it doesn't tell you, did you compress it to stopping? So distance, we don't know. And let's see, mu is 0.5. So high friction coefficient. And then here, was it 5 kilogram per second? And then 100 Newton per meter. Cool. Always helps to like write down, what do we know? Any other initial thoughts? All right. So now, literally with no direction, I'm not going to tell you how to start. What's your first step? Like, just we're just taking one step towards what we think is going to guide us to the solution. And I want to know, I want to know like where do you start from? What are because where you start from kind of outlines what assumptions you made before you started, right? Like if you start with kinematic equations, there's a lot of assumptions that were made where that's true. So let's go from there. Where do you start? That's our question. You're not alone. You can ask other people. I mean, you have to turn in the assignment with someone else. So what do you think? How do you start? What? Assume at rest? Yeah, so they're all dropping half a meter from rest. Yeah. So all three of them are dropping onto these mechanisms from rest and then into our stoppers. Time? Okay. Yeah. Okay.
morning I should have
Go
looked
from there and then we can.
I should have looked at the lecture. So I don't know. It makes sense to me. What is it?
Before they can. How's that right? I was like, the velocity.
It is very nice to
sit there and just like pedal and you go around.
What if you went up a hill?
No, it's like years.
I know that, but it's still
Go
hell.
down. No, if you go down. I swam out there, so I had a big fucking first year. And a really small
You're saying the thing is fun. Biking's easy, guys. That's a fucking bottom line issue.
This is for mountain bikers. The road is there. For mountain biking, you want to be able to get a hill so you can find the access. Oh, hell yeah. You're there to have this fucking snap into your fucking chest, and then you fly over and snap your face. And then you get the balance. If the bike's
You enjoy this shit? I want something like that.
yeah.
I was skating.
Okay. So I went around, saw some different ideas for getting started. Some people jumped into like conservation of energy. Any other takers on that one? Yeah, some energy. I like that approach. Sometimes I feel like this class should start with like conservation of energy, like energy methods, because most of you have just taken thermodynamics and it's still fresh. It's like a nice connection. But I've fallen in, like I rearranged the class a little bit, but it's still kind of like just the old way of doing dynamics. Like first you learn vectors, then you learn all the properties of vectors, and then finally you learn like a vector can be turned into a scalar, and here's energy. And I don't know, that's the way we do it. But energy works. So let's take a look at like just A. We'll say conservation. What does conservation of energy look like as we're dropping something onto a spring? 1/2. Yeah. So so maybe we have like 3 kind of steps. So like when we're talking about like energy, whether it's like thermodynamics, conservation of energy, like all these things, main thing is identify like, what do I start with? Where did I end up? Where I end up could be a function. Like maybe I want to say like, what is my velocity as a function of distance? So maybe I'm starting off with 10 joules. I'm gonna roll down a hill, and I want to know how fast I'm going along the way, something like that. But we could pick exact points of like when I'm here, when I'm here, when I'm here. So I could say like this is state 1. I'm just saying like when there's lots of potential energy from gravity, I'm at state 1, so that's, and we have to choose what H is, but we can put it there. And then we could say 2 is sort of our maximum kinetic, when it's moving the fastest right before it hits the spring. And then maybe 3 would be like kind of squishy spring, something think about this? The nice part about this is that it answers a question of like, how fast is this thing going when it hits our mechanism? Like when it gets to part two, how fast am I going? So we could start there. How does that sound? What do we think? Start there? All right, give it a shot. So what is that V2? That's our first question. How fast are we going?
Rate change equation in an open system. Because they got all this shit. We're solving the velocity at the point that it gets to the spring. The velocity it has. I do remember learning this. Last time I did it, 4 years.
How fast are we going? Yeah.
I have a question.
Yeah.
Would it be like before like 15? Is that how we calculated?
Okay, yeah, like how do we do this? Okay. Well, so did anyone get a number? And then I'll show kind of like at least how I would do it. So what number did we get?
I got so it's B2 3.130.
3.13. I think you got same numbers, right? 3.1, 3.1. All right, so let's take a look at this. We'll say it's 3.1. So how did we get there? At least if we're using energy method. So one way to do this, as I was walking around, people were like, I know you said use energy, but I just use kinematic equations, and like that totally works. And it is the exact same equation. So let's use energy, and then we'll compare that to kinematic. So we have mgh1, Actually, let's start from scratch. T1 plus V1 plus work from 1 to 2 equals T2 plus V2. Every time I write out an energy equation, I write this one first, because this has to be true. T is kinetic energy. We're in dynamics. You're welcome back to physics. Like, T is kinetic energy. It's not KE anymore.
That's gonna kill me.
K is a spring stiffness. It's not kinetic. But anyway, T is kinetic energy. V is potential energy because it's very important. I don't know, but it's there. V is my potential energy. What's that W1 to 2 NC?
That's the work.
Work.
From points 1 to 2.
Ooh, work done going from 1 to 2. It's only on the left-hand side. It's always part of, because it's always describing what happened as I went from 1 and got to 2. What's the little NC? What does that mean? This is kind of, we're like jumping way into like, usually this is module 3 sort of stuff, but why not? We're here, right? It's Friday afternoon, we're all in for some fun. We'll talk about work and different types of work. So NC is called non-conservative. Things like friction, drag, moving through a fluid, like things where you can't get it back after you do it. So think about like when you climb the stairs. When you climb the stairs to get up to this classroom, you needed so much energy to get here. Like what we got now, we are on floor 2. We'll say we're 15 feet up. 15 times 30, whatever, some number. So we use so much. I don't even know. 15 feet. I don't know. But we use so many joules to get up here. We're not going to get that energy back by going back downstairs. Our potential energy goes back to 0 as we go back downstairs, but the chemical energy we used, it was all non-conservative work to get us to this point. So here we are, we sit here with all our potential energy, but we're not going to, it's not like we can skip lunch because we go back downstairs. That's our non-conservative work. Okay, and then T2, V2, kinetic potential. So now I can write, this one starts off at 0. This one is MGH1, non-conservative, nothing happening unless I think there's drag. Usually assume there's no drag, and if you're moving 100 meters per second, then factor in some drag. That's kind of the good way to go about it. Equals, at V2, I'll just call it 0. And then a 1/2 mv2 squared, like this. So if I get rid of mass on both sides, put this 2 over here, (2gh) is v2 squared. This is the kinematic equation that you always forget about, but yeah, there's a v final squared minus v initial squared equals 2a delta x. V initial was 0, v final is v2, a is g, delta x is h. It's the exact same equation. What? So whether you use energy or kinematics, you'll end up with the same equations. Like you get there either way. You always end up at a Dunkin' Donuts. It's New England. You always get to the same spot. Are we out of time? Awesome. That's a great place. We'll pick up on Monday and we'll keep doing some design work. All right. Thanks a lot.